Hello, welcome to another module in this massive open online course. So, we are looking at example problems in convex optimization. Let us continue our discussion. Right, so we are looking at example problems, and let us look at another problem. Problem number 1. So, we want to look at this is a simple problem, minimize C bar transpose X bar subject to the constraint that L bar is component wise, a given vector L bar is component wise less than or equal to X bar, which is less than or equal to another vector U bar. That is, which means that if you have the elements of this vector, let us say L is X bar is an n dimensional vector, then we have L1, L2 up to Ln is component wise less than or equal to your vector x1, x2 up to xn, which is again component wise less than or equal to u1, u2 up to un. That means each Li has to be less than or equal to xi, has to be less than or equal to, or has to be less than or equal to xi, has to be less than or equal to ui. This is not, this is a single scalar quantity. So, this is just your normal equality, and this has to hold for all I equals 1 to 2 up to n. And this is also known as box constraints. This constraint, these constraints, in fact, a set of n constraints, in fact 2n constraints, these are also known as box constraints, because if you look at the 2-dimensional scenario, that is, if you look at a 2D plane, what we will have is that for L1 x1, that is, if you look at x1 and x2, this will mean that x1 is less than or equal to u1, and x2 is greater than equal to, x1 is greater than equal to L1, and for the same matter x2 is less than or equal to u2, and x2 is greater than equal to L2. So, therefore, x1, x2 are confined to this box, that is greater than equal to L2, less than equal to u2, greater than equal to L1, x1 greater than equal to L1, less than equal to u1. Okay. So, they are constrained to this box. So, x1, that is your vector x1, x2 is constrained to this box. Hence, this is also termed as that is, in fact, this is a rectangular box, correct. This is your rectangular box. Hence, this is also termed as box type constraint. In fact, this is a simple optimization problem. This can be solved as follows. Okay. And this is simple. In fact, if you look at it, this is simply a linear objective. This is in fact, this is a linear program, all right. It is a simple linear program. You have the objective function is linear, and the constraints are also linear, correct. So, this is, in fact, if you look at this, this is a simple linear program. This is nothing but, if you remember, a linear program is nothing but linear objective and linear constraints. Okay. And the solution for this is fairly straightforward. It's a simple example. So, if you look at the objective, you have C bar transpose x bar, which is basically I equal to 1 to n summation C I x I. Now, observe these box type constraints make sense only if Li is less than or equal to each Ui. So, we assume here that is Li is less than or equal to Ui. If Li is not less than or equal to Ui, then the constraint no xi can satisfy xi greater than or equal to Li, but less than or equal to Ui, alright, which means the problem becomes infeasible, alright. So, problem is feasible only if Li, that is each lower bound Li is less than or equal to the upper bound Ui for each variable x. So, Li, so for problem to be feasible, this implies Li is less than or equal to Ui, otherwise there is no point x which satisfies the constraints. Now, so we have Li is less than or equal to Ui. Now, consider any x tilde I such that Li is less than or equal to x tilde I less than or equal to Ui, that is any x tilde I which is lying within this interval. Now, therefore, now this implies something very interesting. If Ci greater than or equal to 0, this implies Ci inequality remains changed, Ci less than or equal to Ci x tilde I less than or equal to Ci Ui. Okay. So, minimum value if Ci is greater than or equal to 0, minimum value of over for x tilde I lying in this box is Ci Li, which occurs when x tilde I equals Li. Which occurs for x tilde I equals Li or xi equals Li, that is the minimum over this interval in this box occurs for Li if Ci is greater than or equal to 0. On the other hand, if Ci is less than or equal to 0, now again observe that Li is less than or equal to Ui if that is for any xi, which implies if Ci is less than 0, this implies, now inequalities get reversed, this implies that Ci Li greater than or equal to Ci xi, any xi in this interval which is greater than or equal to Ci Ui, which means this is the minimum value. Minimum value if Ci less than 0, okay. And therefore, the optimal value of each xi, now it is clear, optimal value each xi, this is equal to, well, what is this equal to? This is equal to Li if the corresponding Ci is greater than or equal to 0, and this is equal to Ui if Ci is less than 0. And therefore, the minimum of C bar transpose x bar which is equal to the minimum of summation I equals 1 to n Ci xi. This is equal to summation, you can also write it as summation I equal to 1 to n Ci plus times Li plus Ci minus times Ui, where Ci plus, you can also write this as maximum of Ci comma 0, which is equal to, I am sorry, this is not Ci bar, this is Ci plus. This is equal to Ci if Ci greater than or equal to 0 and 0 otherwise. On the other hand, similarly Ci minus equals Ci if Ci less than or equal to 0, 0 otherwise. Okay. And you can also write it in a compact fashion as follows. You can also write this as, therefore, minimum C bar transpose x bar subject to your constraint, that is the box constraints L bar component wise less than or equal to x bar component wise less than or equal to u bar. This is equal to summation I equals 1 to n Ci plus Li plus Ci minus Ui, which is equal to, you can write this as L bar transpose C bar plus U bar transpose C bar minus, where C bar plus contains all, this contains all positive elements of C bar or contains only non-negative rest are 0, and this also contains only negative elements of C bar minus. Star. So that is the optimal value of this problem. So you can say it's C bar transpose x bar, the minimal value is Ci plus into Li plus Ci minus into Ui. That is where Ci plus equals Ci if Ci is greater than or equal to 0 and 0 otherwise, Ci minus equals Ci if Ci is less than 0 and 0 otherwise. Alright, so this is, although the idea is very simple, it shows you formally how to come up with the solution for a simple objective convex optimization problem like this one, which is a linear program. Alright, let us proceed to a slightly more sophisticated example, which the solution to which might not be very obvious, and that is the following. It is problem number 2. We want to minimize the following, again linear objective C bar transpose x bar subject to the constraint A x bar. Now there is a component, it is not box wise, there is a component wise inequality A x bar component wise less than or equal to B bar. Okay, you can see objective is linear, constraints are linear, therefore it is a linear program, but slightly more sophisticated, and it depends on the solution now very much depends on the nature of A. To make the problem simple, we will say A is a square full rank matrix. This implies that A is invertible. Okay. A is a square full rank matrix, which implies that A is invertible. Okay. And we need to solve this optimization problem. For this, what we do is we substitute substitute Ax bar equals y bar. So, we will set Ax bar equals y bar, which implies that we will convert this into an optimization problem in terms of y. Okay. We are introducing this new variable y. Now, since A is an invertible matrix, there is a one-to-one correspondence between x bar and y bar. So, which means x bar equals A inverse y bar. Okay. So, from x bar one can find y bar, from y bar one can find x bar. Since A is invertible, there is a one-to-one correspondence. Okay. Now, we will write the equivalent optimization problem in terms of y bar. Therefore, optimization problem can be formulated in terms of y bar. So, we have the objective C bar transpose x bar, which is C bar transpose A inverse y bar, and I can formulate this as C tilde transpose y bar, where C bar transpose A inverse equals C tilde transpose, which implies, taking the transpose on both sides, A inverse transpose C bar equals C tilde. So, I combine the inverse and transpose. I am simply going to write A minus transpose, A inverse transpose, which means A transpose inverse or A inverse transpose, both of these are the same thing. A inverse transpose C bar equals C tilde. Okay. So, the objective becomes minimize C tilde transpose y bar subject to the constraints, Ax bar component wise less than or equal to B bar, but Ax bar equals y bar. So, this is constraint will be y bar is component wise less than or equal to B bar. So, now we have a very nice, we have a much more insightful and simpler optimization problem, minimize C tilde transpose y bar in terms of y bar, in terms of the new variable y bar, subject to the constraint y bar is component wise less than or equal to B bar, and this will basically be summation I equals 1 to n C tilde I y I. Okay. And the constraint will be component wise constraint. This implies that each component of this vector y, yi is less than or equal to each component of vector b, that is bi. Okay. Now, it is easy to see what the solution of this optimization problem is. Now, if once again you go back to the, now one can see what the we have reduced it to an equivalent form from which it is simpler to infer the solution. Now, you can again rely on the principles we have seen previously. If Ci tilde, now see, if Ci tilde is greater than or equal to 0, we have yi less than or equal to bi, which implies Ci yi less than or equal to Ci bi, which implies Ci yi, or rather Ci tilde, I am sorry, Ci tilde yi tends to minus infinity as yi tends to minus infinity. Okay. So, implies that I can make the objective, right, by tending that particular yi. So, if any Ci tilde is greater than or equal to 0, I can take that yi to minus infinity, objective becomes minus infinity. So, it is unbounded below. Okay. So, if any Ci tilde greater than or equal to 0 implies, or to be more specific, if any Ci tilde is greater than 0, this is not greater than or equal to 0, if any Ci tilde is greater than or equal to 0 implies Ci yi tends to minus infinity if yi tends to minus infinity, implies minimum value equals minus infinity. Now, if all Ci tilde are less than or equal to 0, if all Ci tilde now you observe that yi less than or equal to bi implies Ci, because Ci tilde is negative, Ci tilde yi is greater than or equal to Ci tilde bi. So, the minimum occurs for Ci tilde bi. And therefore, the met minimum implies minimum C bar transpose, or rather C tilde transpose y bar equals, well, summation I equals 1 to n C I into B I, which is equal to C tilde bar transpose B bar, and we know what is C tilde transpose. C tilde transpose is C bar transpose A inverse B bar, but this is only if each Ci tilde is component wise less than 0, component wise less than 0, or component wise less than or equal to 0, component wise less than or equal to 0, which implies C tilde equals A inverse transpose C bar is component wise less than or equal to 0, and otherwise minimum C tilde transpose y bar equals minus infinity, because if any component of C tilde, that is any component of A inverse transpose C bar is greater than equal to 0, greater than 0, corresponding yi can tend to minus infinity and the objective will tend to minus infinity. Therefore, the minimum value, therefore, now summarizing this, minimum value of this this is equal to C bar transpose A inverse B bar if A inverse transpose C bar is component wise less than or equal to 0, this is equal to minus infinity otherwise, that is otherwise means if any element of A inverse transpose C bar is if any element of A bar inverse transpose C bar is greater than 0, all right. So, that is basically the solution to this optimization problem. What is interesting about this is very insightful. What is a seemingly complex optimization problem can be given, I mean, and the solution to this seemingly complex optimization problem can be found in a very elegant fashion, and it yields a lot of important insights, all right. So, these examples hopefully help you better understand the different aspects or different facets of convex optimization problems, how to solve them, and the valuable insights that they yield, all right. So, let us stop here. Thank you very much.